I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of materials science and engineering. My name is Taylor Sparks, and I am joined today by David Pearman of Lucideon. Now, David is the flash sintering business manager at Lucideon. He has a PhD and a master's, both from University of Birmingham, and he has a business management diploma from the University of Warwick. And he has been at Lucideon for 12 years. So, David, nice to meet you, man. How are you?
Oh, good. Yeah, nice to meet you too. Thanks for having us.
Yeah, pleasure. We are recording this. I am back in Salt Lake City, which is tragic because you are in Stoke-on-Trent, which is not very far from Liverpool, where I've been at for 12 months, but we couldn't quite make our schedules connect to record in person. So the next best thing is these sort of, distance chats.
Yeah, indeed. No, that was a shame. I think it was because we were in the middle of the big office move and building move, and then I rudely had some holiday to take, but
We will forgive you. I don't blame you one bit. Well, David, it's a pleasure to chat with you. A bunch of people have asked us to do an episode on flash sintering. We've done a couple on SPS. We've talked about some general aspects of sintering. So today we're going to talk about flash sintering and why Lucideon is in this space. But maybe before we dive into that and explain what is it, how it works, tell me a bit about Lucideon. What is this company? What are you known for? What are the type of products that you're producing for people?
Okay, so we don't actually produce any products in a sense. We're a development and commercialization company. So I guess we're a advanced materials consultancy, both in the US actually and in the UK. But the UK side, where obviously I'm based, is more advanced ceramics and ceramics expertise. So we help solve problems, whether it's developing new processes, new formulations, or we develop technology platforms and try and sell them on license. So we want to help people out of commercializing technologies out of universities and academia and get them through the technology readiness levels, so through the TRLs up to sort of 6 and 7, where we might be able to deploy them in our with our partners and clients that come to work with us. So yeah, it's quite a varied place.
So it's sort of like a very high-tech consultancy where you are taking these nascent technologies and helping them get to prime time. But a lot of these companies need a partner like you to make that happen. They need that expertise.
Yeah, and so the reason why we were not recording in person was because we were moving buildings, but that's because we've just expanded with a big government funded award called a Strengthen Places grant actually. So we're building an advanced ceramic pilot line. So and as part of that, we formed like the Midlands Industrial Ceramic Group, and so this is a consortium of advanced ceramic manufacturers that can have access to this pilot line we're building, and that's why we needed the space. So that's why we're relocated to Stone, just down the road from Stoke, where the original headquarters was.
That's interesting. So it's federal funding, right? So it's state funding, which means that they want it to benefit more than just one company. So you are allowing other companies to come in and use this advanced pilot line to test new ways of making ceramics, new fabrication techniques, new technologies, and then what do you get out of that? Like, how's that arrangement work? How is this actually, why would you guys agree to do that? Because you're essentially, is it the benefit that you guys also get to develop your tools in-house?
Yeah, so there's all kinds of benefits. So the UK funding system works, I guess, at 60% funded. So Lucidion's actually doing a significant investment in this advanced ceramic pilot line as well. And there's a lot of in-kind support as well. So overall, it's a £42 million project over 4 to 5 years. And 18 million pounds is funded across all the project partners. So we've got technical deliverables and projects we have to deliver during that. And one of the work packages is to set up this advanced ceramic pilot line that will be free access for the consortium members during the project time. Okay. The legacy of that will be that the Midlands is an advanced ceramic hub with an opportunity for people to come and utilize and benefit from this advanced ceramic pilot line, whereas they might not be able to have
Okay.
access to these
Yeah.
techniques, or they can't take their own manufacturing offline. What if they break it doing something new? That sort of thing. So, and within that pilot line is the developments of flash sintering and so on, as you already alluded to. Yeah.
Well, that's kind of a refreshing take on business. I think that's really a forward-looking model where you realize that, yeah, it means that we're going to have to share some resources, but we all sort of benefit from it, especially in the establishment of this hub. Well, this is awesome. This idea of looking forward to the future and establishing, the Midlands as a ceramics hub. And it's not a far cry from the past, right? So I did my PhD. I worked at a ceramics company for years. My PhD was from one of these OG ceramics guys, an English dude from Hull, actually, named Dr. David Clark. Anyways, I went and visited him recently in November, and I was still in England at the time, but I went back for a conference in Boston. So I was chatting with him. He's like, "Have you been down to Stoke-on-Trent?" And I was like, "What are you talking about?" And he's like, "There's this ceramic museum. It was the heart of ceramic, manufacture for centuries." And so, anyways, tell me about this. Is this true? Like, is Stoke-on-Trent really a place that has a storied sort of ceramic past?
Yeah, well, I must admit I have limited knowledge in comparison to some of the Stokies, but yes, indeed it does. So I guess it's known as the Potteries, and I think since the Industrial Revolution, it's been a hub for tableware, whiteware, and traditional ceramics manufacture. And that was actually the birth of Lucideon, was as the British Ceramic Research Association in
So
1948.
why is that? Was it usually when you see something like that prop up, it's proximity to resources like maybe the clay or the minerals that went into it, or sometimes it's access to cheap energy or the workforce, or what was the reason why this place sort of popped up, the Potteries? Can you tell me why is it, well, first off, when was this all happening and what made Stoke-on-Trent this center for ceramic processing historically?
Okay, yeah, good question. So I guess it must have been even back 17th century.
Okay.
It's known as the Potteries, and that's because there's a local abundance of coal and clay and the resources around the Peak District area and around Stoke-on-Trent, as well as the transport network, that being the canals. And then, having recently been to one of the local museums in Stoke, I guess they had the technology as well, in terms of the processability of these materials, but also the formulation to become kind of world leaders as high quality kind of traditional ceramics and tableware.
Okay, fantastic. So how fitting then that from this storied history of the Potteries comes this renovation and this rebirth of ceramics, but now with new technologies and new techniques. And that brings us to the focus of today's episode, which is on flash sintering. So David, can you tell us what on earth is flash sintering? How does it work? Explain it like really simply for us.
Okay, so it quite simply is the application of an electric field to a ceramic during its sintering process.
So how's that
So,
different than SPS? Because that's also an electric field.
okay, yeah, absolutely. So it's a pressureless technique. So we're literally in its simplest form in terms of contact flash. We're sandwiching a cylinder of alumina or zirconia between two electrodes. We're heating the furnace up. The electrodes are just resting on the top and the bottom of that ceramic piece. Heating the furnace up to, say, 800, 900 degrees, applying that electric field, and then seeing a rapid sintering process occur with some optical emissions. For those who've seen flash sintering in progress, it tends to glow quite nicely. And then we're turning off the field and then cooling it down, and then we're assessing the performance of that part. So it's a rapid sintering technique. For many different reasons, whether that's lower energy, whether it's speed of manufacture, or whether actually we can control the mechanisms and the performance of that material in comparison to conventional techniques, is what we're trying to do.
So is this, I think of like arc melting. In arc melting, you've got a really big voltage difference and it actually arcs across a vacuum and that melts your sample. This is not that. You're not dealing with that high of voltages. But my impression is that with flash sintering, you're dealing with higher voltages than SPS. I mean, those can operate at like 10 volts, just really high currents. What's the typical voltage range?
So it can be 1 to 2 volts. It can be a couple of kilovolts. So in comparison to SPS, it's not in a die. So the majority of your current is passing through the sample, not around the die. There's no applied pressure, although you can have applied pressure if you wish to. So therefore, we saw it as a more scalable solution in terms of size of part or multiple parts at once.
But it's not like arc melting where you literally like are directing the tip and you're sort of melting your sample as you go. This needs to be done everywhere all at once, because if it's not, you're going to get cracking, right? You can't have one part of your ceramic sort of sintering the region next to it not. So are there only certain types of shapes that this is amenable to? Can you only do plates, for example?
Okay, so there's a couple of answers there, which is great. So you're correct in terms of contact flash is limited in its geometries. So we have to find the right application for that, and then how we scale that. So it needs an intimate contact with a flat surface, and then indeed you have to have a good thermal management system as to how you're going to make sure that that's repeatable and homogeneous, which is some of the thermal management is one of the brilliant technical challenges in terms of scaling this technology as we go. And our approach to it is having a nonlinear real-time control software. So it's designed to stop in real time those arcs or those localization points, and just provide a uniform system. Also, though, you do mention the fact that is it limited in geometry to that? We have developed a contactless system where we are igniting a plasma and rastering that plasma in sort of, if you imagine a taser, so where you've got that kind of spark between two electrodes. We're trying to essentially ignite a plasma at a low furnace temperature and raster that across the surface. So you could think about using that for thin layer ceramics and coatings, environmental barrier coatings and things like that. So there's kind of two arms to our flash sintering. There's the contact and the contactless, as it were, with different applications that we're trying to scale up.
So I've never done flash sintering, so this is interesting to learn about it, but I'm surprised that you can actually raster it. I would have assumed naively that, if you sinter part of it and then you're passing over next to it, you're really hoping against hope that you're going to get these ceramics to sort of densify in the same ways that you won't get cracking along those interfaces. Is there cracking? Do you tend to get cracking along the sort of pathway of the raster?
Yeah, indeed. So with the contactless, there is geometrical limitations as well. So it has to be a thin sample so as to sinter without inducing too much mechanical strain there as you're getting that shrinkage. So we've sintered and looked at rastering samples, anything from tens of microns to a few hundred microns thick. So things like environmental barrier coatings for the prevention of hydrogen embrittlement on metals, or indeed looking at some coatings on CMCs and things like that. And the idea being is that you can this might be a product enabler. So something you couldn't do conventionally, because to do it conventionally, you'd need to damage the substrate. And indeed, we're just wanting to get a power dissipation in the coating itself and not in the substrate. So it's all about the thermal management then of the plasma instead of the thermal management of the power through your piece. But the software that we're developing is kind of that control and that scale up, that controllability and the prevention of any hotspots.
Okay. Well, we just did an episode on thermal spray with GE.
Okay.
I don't know how familiar you are with it or not, but it's a very similar competing technology, and it has some differences. In thermal spray, essentially, you have a plasma, and you're taking whatever your material you want to deposit, and you're passing it in through that jet of plasma. It's then getting, melted, it's volatilized, and it's being deposited onto the surface. So this is different because here, what you're sprinkling the powder, you're packing it onto the surface, you're painting it on, you're dip coating it, and then one of these methods, I'm guessing, followed by you're bringing the plasma to the material that's already on the surface and you're melting it. So what's the difference in terms of microstructure and properties of these two different techniques?
Yeah, great question. So I won't pretend to be an expert in terms of the thermal spray or the plasma coating for sure, but I would imagine you might use a TBC in terms of a thermal, for a TBC, and then it's got a various porosity in order to provide that thermal conductivity and that thermal barrier protection. With an EBC, I guess where we're looking at a denser coating. So then you're looking at preventing, nitrogen, oxygen. We're looking at really preventing sulfides, from penetrating into that substrate material, or indeed hydrogen. And so, preventing, it's more a preventative environmental barrier coating as opposed to a thermal management. So I think they're not necessarily competing techniques, but they've both got their part to play.
Yep.
And indeed, of course, plasma spray is an industrially relevant and used, whereas our contactless flash is on its way up the TRLs rather than already available. So
Okay.
yeah.
I love it. I love adding sort of tools to they're like arrows to your quiver, right? Like you've got different techniques that are available now depending on what you're trying to achieve. And it sounds like this is going to be for more dense layers, at least in this contactless one. So in the contact one, something you said that caught my attention was you said that you can get local arcing, right? If you have these you have good contact with big, say, plates on either side of it. How do you influence certain parts of it? If one little spot in that plate is arcing, how are you going to mitigate that? Because I assume you're just applying a voltage across the entire plate, not in localized regions. So how are you mitigating that?
Indeed. So I guess the clever folks that work here, not me, I won't claim to have done this, but it's the nonlinear control software. Essentially, you tell it what to do and it will prevent any of those spikes within the tolerances you've told it to operate. So we can pulse current in, we can ramp it slowly, we can do all this. And it also, when it spots in real time, it spots anything about to localize and it'll back off that power system straight away and allow it to re-homogenize. So flash sintering is a material. There's not a one size fits all, right? It's a material driven process. So we have to optimize flash sintering parameters for any material. And if we say do a 6-month study, so one of the great examples that we're working on at the moment is flash sintering for the nuclear waste disposition. So waste plutonium stockpile in the UK. And we started off by making surrogate fuel pellets of Syria because it behaves similar to uranium and so on in terms of its conventional sintering behavior. So we just make discs. So we've got pellets of this, and the first 6 months at the start we'll be blowing holes and melting the middle, right? And then we start to play with these parameters using this software where we're teaching it the limits of the material and how to optimize that. And we might do that by ramp rates, we might do that by pulses, and so on. We can choose how much power we want to get in, how much maximum voltage it is. And then at the end, and of course, another important factor is redesigning that electrode interface. That matters a lot as well, depending on the material you're working with. And then we'll go, 5 months later, we're producing homogeneous pellets, churning them out. Right, and that's a really satisfying kind of feasibility study as to the potential benefit of flash, and then how much time have you saved, how much energy does it cost, and so on.
Why did Lucideon decide to get in the game of flash sintering and other emerging ceramic technology techniques, and what have been some of the challenges you've come across?
Yeah, so when I joined Lucideon, I joined as part of the new technologies group. So this was actually quite a bold punt from the company at the time, I guess, in terms of hiring some fresh faced folks. I didn't even know what a ceramic was when I joined, in comparison to what it is now. But I was tasked with the job of trying to find a technology to reduce energy consumption in the ceramics industry. So after a little bit, and quite coincidentally, it was just as Rishi Raj from the University of Colorado and Marco and Colonia and people had published that first paper on that flash sintering. I think it was titled, rapid sintering of YSZ in under 5 seconds or something like that. And so this kind of just came across I think our CEO handed me this paper and said, have a read of that, like in my first week. And before I knew it, I was sat in the cafe with Marco Colonia with a bag of whiteware in my suitcase, getting that through customs, and just flashing doing some flash experiments with him in the lab and then snowboarding at the weekend. So it was great fun. Yeah. And that's how we started, really. So yeah, essentially we started, and then we won a funding grant, a regional growth fund. And that allowed us to build a team of engineers and material scientists to really try and investigate this properly for tileware. And then Flash at Lucideon was begun. Now the tileware didn't work out, but we learned a hell of a lot along the way, what not to do, and the whole kind of thermal management software and the way we do things now and why it potentially will work for nuclear waste disposition or EBCs was entirely born out of what we learned in forming the team and this basic kind of fundamental IP that we've developed in terms of how to make it. It didn't not work for tileware, but it wasn't enough given that it's a mass manufacturing, low cost, high volume product. Yeah.
Okay, so I think I understand a little bit about the technology. I understand a bit about your role in sort of starting to learn about it and approach it. Now, what I'm curious about is, let's say that you're successful, that you're seeing more and more instances where this technology delivers a good product, maybe at a lower energy, maybe it's a unique microstructure. It just seems promising. How are you going to convince established, ceramic manufacturers that this is something that they should care about and start to actually put into practice? What challenges do you foresee along the way?
Yes, indeed. So I think in order to get this across the line and see this in a factory, I think we work collaboratively with lots of different organisations. So we are an SME from Stoke-on-Trent, and of course we don't make equipment manufacturers. We're not an end user and a manufacturer. So, for example, we work quite closely with academia to do the fundamental research. We have the technology expertise, and then, of course, we need the end users and the engagement. So we work collaboratively with equipment manufacturers, and we have scale-up designs on paper ready as we start to overcome some of the other technical challenges. But then there are technical and commercial challenges, I guess, to overcome along the way. One thing we have to do is prove that it works on a 1 or 2 sample scale, as we're doing and have done for a few applications. But then once you have that, I guess it might be worth thinking about other technologies that have emerged in the last few years that have had some skepticism and are finding their niche in materials. So I guess additive manufacturing, 3D printing is one of them, where to be used commercially, that has to be looked at part by part and qualified part by part basis. And it's the same for flash, right? You're applying an electric field to an individual piece of ceramic. So that has to be quality controlled for each individual part. I think traditionally ceramics in bulk manufacture, a lot of the systems that they have in place, thermal management within the huge furnaces, they're kind of a given because historically they've always been done that way. But as soon as you start rapidly sintering it piece by piece, you want to know what's happening on that. So I think there'll be a large sort of quality control issue, and ways of monitoring that will both be a commercial and a technical challenge. But the biggest one really is at the moment is the thermal management and that repeatability of mass producing these samples within the geometrical limitations that we have. So that's why we're targeting and a focus on kind of that nuclear sector where the geometries for the contact flash are unique and suitable for the technology, and then the coatings or things like solid state electrolytes or cathode systems in batteries as well, where the contactless can come into play.
It seems to me like one of the challenges you're going to address with that is, if you do understand how thermal transport is going to come into play, it's going to depend on how the green powder is placed on the surface of these things or between the plates and how well it's distributed. One of the benefits of SPS is that you're squeezing it, right? So there's like this mechanical deformation, which is not uniform, right? It's definitely not uniform. Like you learn this in the basic ceramics course that there's die-wall friction, there's gradients, but at least you're influencing it a little bit. Here, how are you making sure that the powder, let's say you're doing contactless, right, that it's being evenly distributed at first, such that when you pass it over and raster it, you're getting a more even, film created? I'm curious. This seems like an open area where I wouldn't know how to solve that.
No, well, indeed. I guess then you bring it back to the beginning of the talk where we talk about the pilot line that we're developing. So I guess it goes hand in hand with what's the formation technique in the process. Are you designing a process for flash sintering? Are you designing a material for flash sintering, or are you trying to make flash sintering work for a process? So it depends on where the client or the end user is at in terms of their product life cycle. So I think flash sintering, getting involved at that early stage, such as for solid state electrolytes or some battery materials, new emerging systems, is a great way, because we can then design and use that pilot line. And how many different ways can we dip coat it? Can we tape cast it? Can we, and then we apply flash to it and do a proper study as to how that's affected. So yeah, that's what we'll do in terms of identifying applications for flash and then designing a process for it, because it's a great question that we don't yet have all of the answers to. Yeah.
Okay. As you were describing this, something came to mind. You mentioned, additive manufacturing. Has anybody done the contactless flash sintering in an additive manufacturing sense, where you're putting down a very thin film, rastering, sintering, putting down another thin film, rastering, sintering? Can you combine these things? I've never heard of it. I assume it's possible, though.
Indeed. Yeah, we have started. You've stumbled across one of the.
Cool.
Actually, we had an Innovate project last year where we're looking at again trying to print that thin layer, and then how do you and we have scale up designs. We work with a company, KWSP, in that consortium, and University of Loughborough, where we were looking at 3D printing battery interfaces, 3D battery electrolyte interfaces for maximum surface area with cathodes. And trying to sort of print and sinter. So very early stages that application, but you've already hit one of the ideas. Yeah,
that's cool. I'm very anxious to hear more about that and hear if it actually works. We've done episodes with GE about additive manufacturing where they talked about trying to print ceramics, and they're doing more like the binder jet approach, not this, but it seems like a cool competing approach, and maybe it's going to work even better.
Yeah, there is a team working on the additive here as well. With a lot of developing formulations for robocasting and many other techniques. But yeah, it's an exciting space for sure.
Yeah, it's funny. Ceramics it is literally the Stone Age, right? These are bits of rocks that we find ways to squeeze together and fire and bond. And we are still, thousands and thousands of years later of humanity finding clever ways to do that process better, more efficiently, to get better properties out of it. And Flash is just the latest in a long line of innovations there. So it's cool to see Lucideon, right, diving into this space and enabling this technology even further.
Yeah, a long line of rock welders.
Absolutely. Okay, well, it's a pleasure to have you on today, Dave. Thanks for taking the time to chat with us. We appreciate it.
Yeah, thank you very much for having me.
Okay, we'll talk to you later.
Cheers. Bye.
If you want to keep up with the rapid advance of technology, you'll encounter materials challenges in performance, in energy demands, in cost. You need innovative thinking from a trusted partner that delivers results. At Lucideon, we're materials magicians. From metals to ceramics to polymers, we understand your products down to the atomic level, and we can make them work in ways you may never have imagined. We ensure medicines and nuclear reactors stay safe. We reduce our clients' energy consumption and verify their CO2 emissions. We keep aircraft engines turning and the world's most iconic buildings standing. We make sure replacement orthopedic joints stand the test of time. We even have some of our products on Mars. We take projects from the outlandish world of ideas and scale them through to sustainable production, and thus make the world a materially better place. Lucideon offers you the best of both, jaw-dropping innovation and commercial know-how. So when you're asking the questions, is it possible? Will this work? Just come to us. Go to lucideon.com for more details.
The Materialism podcast is also sponsored by Materials Today. Visit materialstoday.com to stay up to date with the latest happenings in materials science and read some of their awesome articles that they publish. For example, in today's episode, they have an awesome article that we're going to link in the show notes on a novel multi-phase flash sintering technique for 3D complex shape that just came out last year. So you can take a look at that. I think it's be related to the topic that we covered today. You can also head over to elsevier.com and find out more about their journals in general, their conferences, books, and related programs. We're grateful that they've been a longtime sponsor of the show. Special thanks to everyone who listens to this podcast. As you know, it would really be awesome, and we would love it if you would give us a review. That is how other people find the show. So whether you're listening on iTunes or Spotify or Google, wherever you find your podcast, if you like it and you want to help us help more people to find the show, consider leaving us a review. We'd appreciate it. As always, we love to interact with our audience. You can find us, we're most active on Instagram. So if you go to the @materialism.podcast page, you can chat with us, suggest new episodes, see the nonsense that Jared is posting there. And obviously, special thanks to Alphabot and Kolobyte, who make the music for this show. We appreciate all they do. They make really cool music. We think you should check them out. And thanks so much for joining us. We'll talk to y'all next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.